Let everyone join, then we will start. I hope my screen is visible.
Yes, ma'am.
Okay. Okay, let's start. Okay. So, students, to get the wave function, what we will do, we will assume helium atom is equivalent to two hydrogen-like systems. Okay. So, the wave function, how to write the wave function now? The wave function for two electrons which is at distance r1 and r2. Okay, it will be written as this is for ground state, means for 1s. Okay, that will be equal to the product of wave function for electron 1 which is at distance r1 into wave function for electron 2 which is at distance r2. Okay, in this way we will write the wave function. This it represents the wave function of helium atom. Okay, it represents the wave function of helium atom. But what we have assumed that helium atom is equivalent to two hydrogen-like system. Okay, so this is for first hydrogen and this is for means first hydrogen and second hydrogen. Okay, or for first electron and for second electron. Now we know from our previous derivation of hydrogen atom that psi1 s for electron 1 at distance r1 is equal to under the root, here I will write z cube. Okay, for hydrogen z was equal to 1, that's why we have not included z. Otherwise the wave function is z cube upon pi a naught cube, and exponential of e raised to power minus z r upon a naught. जो आपने पहले लिखा था वेव फंक्शन हाइड्रोजन डेरिवेशन में, दैट वाज इक्वल टू 1 अपॉन अंडर रूट पाई ए नॉट 3/2 e raised to power minus r by a naught. यही लिखा था ना? Because for hydrogen z equals to 1, that's why we have not written z. Okay, but for helium atom we have to mention z here. Actual formula is this. Similarly, okay, this is for R1. So here we have to mention that this is R1. In place of R, you have to put R1. Okay, similarly for second electron, which is at distance R2 from the nucleus, what is the wave function? Z cube upon pi A naught cube exponential minus Z R2 by A naught. Okay, now use these in this fourth equation. You can mention it as 4a and 4b. So by using 4a and 4b in equation number 4, you will get, wait. Okay. So you will get psi1s r1 r2 equals to z cube by pi a naught cube e raised to power minus z r1 by a naught into Z cube by pi A naught cube exponential minus ZR2 by A naught. Okay, we will write this wave function in atomic units. Now in atomic units, as I told you, in atomic units, we take A naught equals to 1. Okay, so everywhere A naught, where A naught is present, just put it equal to, approximate equals to 1. And the final form of the wave function will be equal to, we have this term twice, so under root will be removed, so which will be written as Z cube pi, A naught cube is gone because we have put one value. Okay, then e raised to power, and also we put Z is equal to 2, which is the atomic number of helium. So A naught is 1, A naught is 1 here. Okay, here also A naught is 1. Then we will write minus of 2, okay, Z equals to 2, and R1 plus R2. This is the wave function for helium atom. Or you can write psi naught. Okay, psi naught. Everywhere write psi naught. I hope this is clear. So Hamiltonian we have found. We have also found our wave function. Okay. Okay, now we can write the Schrodinger wave, as we are assuming that helium atom is equivalent to, मैम e raised to power 2 है या z लिखना है, e raised to power 2 लिख दिया मैंने 2 यहाँ पे, ठीक है, -2 R1 plus R2. Okay, so as we have assumed helium atom is equivalent to two hydrogen like systems. Okay, then we will be having two equations. For electron 1, the Schrodinger wave equation is, how to write? You know, it is equal to del 1 square psi plus, yes, 8 pi square m over h square e minus v equals to 0. Okay. You know, potential energy for electron 1 is equal to, here also we put psi naught, plus 8 pi square m upon h square e, and potential energy is Z square upon R1. Okay, similarly, we can write this same equation for electron 2 also. Electron 2 also. So that will be equal to del 2 square psi naught plus 8 pi square m upon h square e plus, here we have to mention E naught 1 and E naught 2, which is the energy of electron 1 and electron 2. Z square upon R2 equals to 0. Okay. I hope these two equations are clear. Yes, students? Are these equations clear? Okay. Okay. Now we will try to find out the energy of helium system. Okay, you know, we have seen that the Hamiltonian for helium system, it consists of two parts. First is the Hamiltonian for unperturbed system, and second is the perturbation. Okay, for H naught, we have assumed that this is equivalent to two hydrogen like system. Okay, for electron 1 and for electron 2, we have seen the Hamiltonian. Okay, and we have seen the equation. Okay, so when we apply this Hamiltonian on the wave function, you will get E naught. You will get E naught. Okay, and E naught is equal to, because E naught represent the unperturbed energy for helium atom. And we have assumed helium atom equivalent to two hydrogen like system. So its energy also, it will be divided into two part. First for the first electron and second for the second electron. Okay. So the energy for two hydrogen like system, it is given by minus Ze square by 2. The energy of the hydrogen atom, it is given by minus Z square by 2. And similarly for the second electron also it is Z square by 2. So what is the energy for the unperturbed system? It is minus Z square. Okay. So for this part we have found the energy. You will have to write the direct result. This is the energy for hydrogen atom minus Z square by 2. Okay. Now coming to the H dash part. Okay. See, we have a Hamiltonian. Corresponding to this, we will be having energy E. Okay. Corresponding to this Hamiltonian, we will be having some energy E naught that we have found, minus Z square. Similarly, corresponding to this H dash, which is the perturbation, we will be having some perturbation in the energy too. So we want to find E dash. Okay. So let's find out E dash. So what is E dash here? E dash represent first order correction in the energy. And in the previous derivation that we have done in the class, we have seen that E dash, which represent first order correction in energy, is equal to the integration psi naught corresponding Hamiltonian, or psi naught star you can write, psi naught d2, right? This way we find the first order correction in energy when there is a perturbation. Okay, but we are doing it for helium system now. You know, for helium system we have two electrons, so we have to put two integration sign. Okay, here also we have to put d2 1 and d2 2. Okay, so now write down the wave function expression here, and h dash expression here. We know h dash is equal to, yes, 1 upon r12. Okay, so we will write E dash equals to double integration. H naught is, it was equal to h cube by pi e raised to power minus 2 r1 plus r2. यही था. Into h dash. H dash is 1 upon r12. Again, wave function. Because your wave function is real, so psi star, this star will not change anything in the wave function because it is real. E raised to power minus, again 2 r1 plus r2. Okay. Now we can write it. Okay, d1 and d2 also we have to mention. d1 and d2. So E dash equals to, here we have z cube by pi and z cube by pi, which can be written as z6 by pi square. Okay, we have two integrations. So in the first integration will be for first electron, and second will be for second electron. Okay. In the integration, we will write e raised to power minus 2 r1 plus r2 into 1 by r12 e raised to power minus 2 r1 plus r2 d1 and d2, where d1 is equal to you know it is equal to 4 pi r1 square. Yes, dr1. Okay, like we had written for hydrogen atom. d2 is equal to 4 pi r2 square dr2. Okay, so here we are not going to solve this integration. Okay, here limits are from 0 to infinity. We will directly write the result, right? So e dash, because this integration, the solution of this integration is very tedious, it is very complex, so we are not going to solve it. We are only interested in the result only. Okay, so we will write the result. So because e dash corresponds to the repulsive energy that takes place between two electrons. Okay, if it is a repulsive in nature, hence the energy that will be coming out will be positive. So the energy that you will get after solving this integration will be equal to 5 by 8 into z, and it is positive. Okay, why it is positive? It corresponds to repulsive interaction. Repulsive interactions between two electrons. Okay, so these repulsive interactions are responsible for the perturbation in the system. So now we have found the energy for perturbation. Okay, so we know the energy of helium atom, it consists of two energy term. One is E naught and second is E dash. E naught is the energy when your system is unperturbed. Okay, and E dash is the energy when your system is perturbed due to the inter-electronic repulsions between electrons. So E naught we have found that it is equal to minus of Z square, and E dash is equal to 5 by 8 into Z. It is in atomic units. Okay, this is the energy in atomic units. Now we can write it as, you can take minus common, minus Z square, minus bracket start Z square minus 5 by 8 into Z. Okay, so this is the energy of helium atom. But this is in atomic units. Okay, so here we will find out the energy in electron volt also. So let's see. If we have used your rest of the parameter as such in the derivation, then your E would be equal to in atomic unit, this is the energy. Okay, if we remove the atomic units, then the energy would have equal to 2a naught square. Okay, so by substituting these values, we can get the value of energy for two electrons. Okay, if you want to find out energy in electron volt, so here we have considered that helium is consist of two hydrogen-like system. This is first hydrogen-like system, this is second. Okay, and for hydrogen, the energy in electron volt, it is equal to minus 13.6. For this also, energy is equal to minus 13.6. Okay, so what will be the energy? If you add it, you will get 27.2 something, 27.2. Okay, so what we will do, we will multiply this factor minus Z square, because energy depends on charges also, into minus 27.2 electron volt. You can solve it, okay, and you will get that this energy is equal to something 74.8 electron volt with a negative sign. Okay, so this is the energy of helium atom that we have calculated by approximate method. The actual energy of helium atom, it is approximate minus of 78 point something. So you can see the difference. This energy is calculated by experimental techniques. Okay. And this is the theoretical, we have applied some theoretical method to find out the energy, which is very much approx to the actual energy of the helium atom. Okay. So that's why these methods are known as approximate methods, because these gives the approximation of the energy value to the true value. These methods do not give the exact value. Okay. I hope this topic is clear. Yes, students.
Yes, ma'am.
To everyone, any doubt? Any doubt in this topic?
मैम इसमें हमने ये म्यू ई स्क्वायर और बाय 2a स्क्वायर की वैल्यू सब्स्टिट्यूट की है.
हाँ, yes. For this, this is equivalent to energy of electron. If you check, energy of electron is given by this type of expression, which is equal to minus 13.6. But we are considering helium as 2 electrons, so we have to add.
Okay.
Okay, energies can be given in different units, in electron volt also, in joules also, in calories also. So this we have calculated in electron volt. Okay. Now after doing this perturbation theory, we will start with variation principle. Okay, it will take 10 minutes only. So the derivation for variation principle we will do tomorrow. So Sunday also I'll take one lecture, but in the morning. Okay. Will that be fine? And that lecture, your whole section will have to attend section 1 and section 2. Tomorrow also I'll take one lecture, okay, of 1 hour, in which we will complete variation principle.
Okay.
And in the class we will do the numericals and the questions. Okay. So derivation हम time waste नहीं करेंगे class में. We will directly do the question that are important for 5 marks. Okay. So let's start with the variation principle. We'll give it a brief introduction. So variation principle is second approximate method. Variation method. Variation method is also known as variation principle. Okay. So in variation method, suppose if we have, variation method is used to find out the approximate energy, because it's approximation method. Okay. It is used to find approximate energy, which will be very close, to the true value, very close to true value, true energy value. Okay. Now suppose for any system, exact wave function is known, which is psi naught. This is the exact wave function. Okay. So if we apply Hamiltonian on this, it will give the exact or true value, right? This is the case when we know the wave function. But in variation principle, Hamiltonian is known. Hamiltonian is known to us, but wave function is not known to us. But wave function, please do not just write h only. Do not mention h naught. But psi will be unknown. So in these cases, we apply variation method. Okay. So in variation method, because exact wave function is unknown to us, so we choose trial wave functions. We choose trial wave functions. Okay. We choose different trial wave functions for a particular system. And suppose we have selected psi1, we have selected psi2, psi3, and psi4. Okay, these are the trial wave function that we have selected for a particular system. And we know Hamiltonian is known to us. So we apply Hamiltonian on these wave functions and we get the energy values. Okay, we get the energy values. Now, which wave function will be the best approximation? Because we have selected 4 different wave functions that are giving different energies. Okay, E1, E2, E3, and E4. And E naught is the ground state energy or the true value of the system. Okay, so which wave function will be acceptable or best approximation? Now, suppose this is how we will select. Suppose this level represent E naught. Okay, and these are the energies that we are getting from trial wave function. Suppose this is E3, this is E1, this is E2, and here we are getting E4. So, student, the energy that will be close to E naught, that corresponding wave function will be the best approximation to that system. Okay. So variation principle always gives you the upper bound to the ground state energy. So we got different energies. Okay. Out of these 4, E3 is the energy which is close to E naught. And corresponding wave function is psi 3. So in this case, this psi 3 is the best approximation. So this is your variation principle. That variation principle gives energy which will be upper bound to ground state true energy value. Okay, that means the energy that we are getting from variation principle, it will always be greater than or equal to E naught. But it can be greater, it can be equal, but it cannot be less than E naught. Okay, this is the very important statement of variation principle. This thing you will have to mention, that variation principle always gives the energy that will be upper bound to ground state energy of the system. Is it clear? Yes, students? Okay. But the thing is how to find out energy with variation principle. Find कैसे करेंगे? Theoretically. Because these are the theoretical problems, right? So how to find energy theoretically? So energy we can find from the postulates of quantum mechanics. We use the postulate of quantum mechanics. You know, if we know Hamiltonian, okay, and we choose some trial wave function like psi, we have chosen psi. If it applies to this Hamiltonian, if it applies on the wave function, we get some eigenvalue, E, right? Multiplied with the same wave function. Okay. So this is Schrodinger wave equation. What we do, we multiply on both sides by psi star on psi star and we integrate the equation. Integrate on both sides. Okay. So E is the energy, can be taken out from the integration sign. Here we get psi star into psi d2. So energy E equals to psi star h cap psi d2 divided by psi star into psi d2. Okay. So in this way, we find out the energy by using the variation principle. But here we have some important points, that your wave function will be the trial wave function, psi. Wait. Wait. The trial wave function psi, it will always be some linear combination of some atomic wave functions. Okay, means it will be like this, linear combination of the wave functions psi 3 psi 3. Okay. Or this can be equal to c1 psi 1, or this can be equal to c1 psi 1 plus c2 psi 2. Okay, this kind of wave functions are selected. These kind of wave functions are considered as trial wave function. Okay, which include some parameters c1, c2, c3. So c1, c2, c3, these are known as variational parameters. Variational parameters. Okay, which are adjustable. We can adjust these parameters in such a way to get minimum energy. Okay, we can adjust these parameters to get minimum energy. That will be the best approximation to ground state energy. Clear? So by this formula, we will solve this integration and we will get the expression of energy. Now this energy expression will be having some variables like C1, C2 and C3. Kind of variational parameter will be present in the expression after solving this integration. Okay. Then what we will do, because we want to find a minimum energy, okay, which will be very close to ground state. So what we will do, we will minimize the energy with respect to C1. For that we will find differentiation of E with respect to C1, then we will put it equal to 0, and we will again find differentiation with respect to C2, and we will put it equal to 0. So from here we will get the values of C1 and C2. Okay, these will be the minimum values of C1 and C2, and that we will put here to get the energy. That will be the best approximation. Okay. So in a variation method, we follow few steps. What are these steps? So there are only 4 steps. Just write down. Steps in variation principle or variation method. So first step, it is to choose or to select the trial wave function. This is our first step. To select the trial wave function. Okay. Second, evaluate the integral. Evaluate the energy integral. Here you can mention the integral in the bracket. Integral psi h cap psi divided by psi star psi d2. Okay, in the second step, you will evaluate the integral. In the third step, after the evaluation, what you will do? We will minimize the energy. Okay. After evaluation of the integral, we will minimize. Then third step is the minimize. Minimize the integral. Minimize the integral with respect to variational parameters. Variational parameters जो भी हमारे वेव फंक्शन में प्रेजेंट होंगे, इधर C1, C2 और A1, A2 और AB. So we will differentiate energy expression with respect to C1 if C1 is present, and with respect to C2, and then individually we will put these equal to 0. Okay. Now in fourth step, after getting C1 and C2 values, okay, what we will do, we will find out that which wave function is the best approximation. So the function psi, we will write the function psi with optimum value of the parameter, means minimum value of the parameters, is the best approximation to true wave function and lowest value of energy is the nearest approximation. No, my pen is not working. Yes, lowest value of energy is the best approximation to true energy. So here we have finished variation principle, introduction to variation principle. Okay. I hope variation principle is clear. In variation principle, we have to follow 4 steps. First, we will choose our trial wave function. Second step, we will evaluate the energy integral. Third, in the energy expression, there will be some constant values, either C1, C2 or in form of A1, A2 or AB. Okay, if C1, C2 parameters are present, we will differentiate our energy with respect to C1 and with respect to C2. We will put it equal to 0. Then we will evaluate what is C1 and what is C2 value. Okay. So after putting C1, C2 value, we will get some energy that will be very close to your true value. If it is close to true value, that means that corresponding wave function is your best approximation. Okay. We will do this derivation tomorrow. Fourth step. Okay. So in third step, what we are getting? We are getting C1, C2 values. Okay. So in the fourth step, the wave function with optimum value of the parameters, mean the minimum value of the parameter we will get from step 3. Okay. So we will put these parameters in wave function also, in energy expression also. So the wave function with optimum value of the parameter will be the best approximation to the true wave function, and that lowest energy will be the best approximation to the true value of the energy. Okay. See, we choose different wave function. We will choose psi1, psi2, psi3, psi4. Okay, we apply variation method. So in every wave function we will get some C1, C2 value. तो जो भी C1, C2 put करके हमारे पास minimum value आएगी ना, that corresponding wave function will be best approximation, and that minimum energy will be the best approximation to true value of energy. Okay, so these are the only steps. Okay, now time is going to end. It's less than 1 minute. So I have completed the topic also. Tomorrow in the morning, I will share the link.